In the last video, we left off with a problem that cannot be solved with the law of sines. In that problem, we had a situation where we had two sides, one of length 80 and one of length 90, and then we had the angle between them, the included angle. So that was a side angle side setup. The side of 80, the angle of 79, and the other side of 90. The reason law of sines doesn't work becomes pretty obvious as you try to solve it with the law of sines. You'll notice that you have a 79-degree angle, but you don't have a side across from it. You have a side of 80, but you don't have the angle across from it. And you have a side of 90, and we don't know the angle across from it. So if you were to label the sides of the triangle XYZ, for example, so that this side was little x, you could write that sine of 79 degrees divided by x was equal to sine of y divided by 90, and that of course is equal to sine of z divided by 80. But every single ratio that we wrote there, each one of them, has a different unknown. So there's no way to pair two of those ratios to write a proportion with only a single unknown that we could identify and solve. So at that stage you can tell you're stuck and that law of sines won't work. So law of sines won't apply. It cannot help us here. There's actually another situation that's quite common where law of sines also doesn't help, and that's where you know all three sides of a triangle, but you don't know any of the angles. Obviously, if you know all three sides and you don't know any of the angles, you can never create an angle-side pair, which is precisely what you need to be able to do in order to proceed with the law of sines. Thankfully, side angle side and side 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 are the perfect situations for the law of cosines. So this video is going to show you how to prove and then use another rule that can help you out with these two situations. We'll use the law of cosines in both of these. Okay, so we'll start off with a proof of the law of cosines. Here's our proof, or derivation, whatever you want to call it. We'll start off similarly to how we did the law of sines, which is just an arbitrary oblique triangle, and I'll call it A, B, C, with sides little a, little b, and little c. And just like in the proof of the law of sines, since I don't have a right triangle, I'll create two of them by dropping an altitude. But this time, instead of trying to relate the sides and angles of A, B, and C through sine ratios of those two right triangles, what I'll do is I'll notice that this base here, side B, has actually been cut into pieces when I drop that altitude. So this is just me labeling segment AC as side B, so I can see that that entire length is side B. And what I want to do is I want to focus on the different parts of side B that I've created. So let's take a look at this triangle on the right-hand side. The base of that triangle has a portion of side B, and well, I noticed that that side there, that portion of side B, is adjacent to angle C. So that means I could write that cosine of angle C is equal to its adjacent side divided by its hypotenuse, and I could solve that for the adjacent side. So A cosine C is equal to this little portion right here of side B, stemming from the base of the altitude until vertex C. And what that means is on the right triangle on the left, the other portion of B I can describe as B minus A cosine C. Okay, and this is the setup for deriving the law of cosines. To complete the work, all I do is I use the Pythagorean theorem on these two right triangles. So I have a right triangle that yellow one there, and then the other one is the blue one here. So let's start with the yellow right triangle. In the yellow right triangle, according to the Pythagorean theorem, a squared, the hypotenuse squared, would be equal to h squared plus a cosine c squared. That's just applying the Pythagorean theorem to the right triangle on the right. When I move to the blue triangle on the left and apply the Pythagorean theorem, I'll get c squared equals h squared again, plus this binomial b minus a cosine c squared. Right. So I now have two equations with lots of unknowns. I don't really want those h squareds involved. That's really just a means to an end. So a good idea would be to subtract equation 2 from equation 1 and thus eliminate the h squared. So when I do that, on the left side, a squared minus c squared, so subtracting equation 2 from equation 1. On the right-hand side, just point out again here that the h squareds will eliminate when I subtract the top from the bottom from the top, and then you'll have over here you'll have an a cosine c squared minus b minus a cosine c squared. That second one's a binomial. So as I start to simplify this algebraically, I'll see that I get a squared cosine squared c minus this binomial squared will be the first term squared minus two middle terms, which would be the product of b and a cosine c. So that'd be 2ab cosine c plus the last term squared, which would be a squared cosine squared c. Then I go and I distribute that negative and hope things start to clean up a little bit. So you'll have a squared cosine squared c minus b squared plus 2ab cos c minus a squared cosine squared. Okay, good. That shows me there that I do have some cancellation with a positive and a negative a squared cosine squared c on both sides. So I get back to it, simplify it a little more. And at this stage, we've effectively derived the law of cosines, just a little bit of rearranging to make it look more familiar, or the way most people write the formula. Bring the b squared to the left, bring the c squared to the right so it's positive, bring the 2ab over here with the other ab terms. In fact, most people would write the formula this way: c squared equals a squared plus b squared minus 2ab cos c. The reason people prefer to write equations one way over another usually comes down to, well, how is it easy to remember? Can I write it in a way that it's kind of familiar to me? And if you look at this equation, you'll notice that it looks, well, almost exactly like the Pythagorean theorem. And that's a good way to remember it. The law of cosines, the cosine law, says that in any triangle, oblique or right, c squared is equal to a squared plus b squared minus this little, I call it an adjustment factor, 2ab cosine c. In the case where c is a right angle, c is 90 degrees, cosine of c is then 0, and that adjustment factor just kind of wipes out, and we just have the regular old Pythagorean theorem. And the case where c is not a right angle, then cosine c interacts with this adjustment factor to make the formula work out. You can also think about the fact that when c is an acute angle, I would be subtracting a positive number because cosine of an acute is positive. When c is an obtuse angle, you'd be subtracting a negative because cosine of an obtuse angle between 90 and 180 would be a negative number, so you're adding a little more. And that makes sense with the geometry of the problem. So let's try a quick example. Let's just say we're going to solve a side angle side with the cosine law. So let's say I have a side of length 15 and then a side of length 12 and an included angle of 80 degrees. And I would like to know this side across from the 80-degree angle. So again, the way I know it's a side angle side and not like a side angle is that I have two sides and the angle between them. So the ordering there is important. In fact, in using the cosine law, I'm trying to decide, what should be A, what should be B, what should be C. In this particular case, it's very important that you think about the angle that you know, the 80 degrees here, as the angle that you're going to use in the formula. So that would be C, the angle C in the formula, and that means that the side X here would be the term on the left-hand side, the C squared, so to speak, in the formula. I think I neglected to mention that, but in the cosine law, while it looks like the Pythagorean theorem here, there's no reason that the C here must be the largest side in the triangle, because we're not even necessarily dealing with triangles that have a largest side anymore. Okay, so here's our example. I would write that x squared is equal to 15 squared plus 12 squared minus twice, and that 2, a very common mistake is leaving out that 2, twice 15 times 12 times the cosine, and that's probably the second most common mistake is writing sine instead of cosine, just because you're so used to doing law of sines problems at this point, cosine of 80. So then that means that x squared is equal to, if you work out the details here, 2 times 15 times 12, and making sure you're in degree mode, you get that x squared is equal to 306.5, and probably the third most common mistake is forgetting to take a square root. You get that x is equal to 17.5. So then using that x, I could then use the law of sines to go back and figure out the angles if I like, and I could fully complete the triangle. Another example, let's say another example here, where I have a side cosine law problem. So let's just say I have a triangle, and I know 3 of the sides, and I'd like to know the other one. So let's just say, let's say I have maybe I have a 41, and then I've got a 40. And I realized what I said, and then an 8 there. I said a minute ago I have 3 of the sides and I'd like to know the other one. I meant to say I have 3 of the sides and I'd like to know an angle, since we only have 3 sides. So I've got a 41, a 40, and an 8. Okay, and let's just say I'd like to know this angle right down here across from the 41. Okay, so that means when I'm using my cosine law, sure, I could label everything if I'd like A, B, and C, but the important thing is when I'm thinking about my cosine law, whatever letters you might choose to use for the labeling, that the angle that you're after, in this case, the red angle down here, angle C, needs to be paired clearly with the side across from it. Everything else is symmetric. So I would say here then that 41 squared is equal to 40 squared plus 8 squared minus 2 times 40 times 8 times the cosine of C. And I would solve that equation right there for the cosine of C. So that would be 41 squared minus 40 squared minus 8 squared equals negative 2 times 40 times 8 cosine of C. And then 41 squared minus 40 squared minus 8 squared is equal to 17. So that would be 17 equals, and this would be negative 640 times the cosine of C. And then 17 over negative 640 would equal cosine of C. So C would equal cosine inverse, we'd have to use here, of course, because we're solving an angle, of 17 over negative 640. And again, making sure you're in degree mode there. You get that C is equal to 91.5 degrees. And I picked that particular problem right there. You might, when you think of 41 squared and 40 squared, maybe not. Maybe you typically think of the other side here, not an 8, but if you think of a 9, if I put a 9 there, then that would be a right triangle. I put something slightly smaller than the 9 to give me a triangle that was I knew would be obtuse, because I wanted to point out that the cosine law will solve for an obtuse angle. And that is a nice feature of the cosine law whenever possible. If you suspect that you might have an angle like this one, right, it might be greater than 90 degrees, use the cosine law if you can, because the sine law won't find the obtuse angle and sometimes can lead to an error. All right, that's it about the law of cosines.